Welcome all. In today's video, we will be talking about diode capacitance. So, capacitance you already know. What is capacitance? So, capacitance generally at 12th class we have at least studied it is Q by V, right? Q is equal to CV, right? However, this is for those systems where the capacitance is constant, okay? But if capacitance is dependent on voltage, as in case of PN junction diode, because in PN junction diode, when we apply a reverse bias, these junctions are actually varying. These junction width W is a function of applied voltage VR, right? Reverse voltage VR. And we have to calculate charges over here, right? So here you have some positive charges, here you have some negative charges, right? So as this W increases or decreases with reverse bias, and hence the charge, and that's why the capacitance of system in general, this is not for a dynamic system, but capacitance is defined as for a system if we are applying a voltage V and there was some charge Q plus and minus Q, right? And if we change this applied voltage with very small amount, let's assume dV, because of this change in applied potential, the system has a property that it can store little more charge, right? So this capacitance of the system is defined as dq by dV. Okay. If let's assume q is dependent on many other factors, then the exact equation will be del q by del V. This is how the capacitance is defined. Now, here in case of PN junction, we have two types of capacitance. Okay, one is the depletion capacitance, which we are discussing in this video. There is one more capacitance that is called the diffusion capacitance. Generally, it is present in forward bias. Okay. In reverse bias, this diffusion current is very small and also the diffusion capacitance. So in this video, we would be talking about depletion capacitance. So let's see what exactly happening inside the junction when we are changing a slight reverse bias. Right. So let's assume this was the initial state where p-type doping, that was Na, and n-type doping was Nd. If we plot the charge density, let's assume this was the junction area. So that will differ Xp and Xn with the value of Na and Nd. Right? So if you want to draw this, the charge concentration is 0. So this portion is neutral. This portion will be slightly negative and this side will have positive charge concentration. This is the case of abrupt junction. If you would be deriving the same equation for linearly graded junction, the equations will be different. So this value is, what is the charge density over here? That will be E into Na. On this side, it will be E into Nd. So this is the charge density, okay, per centimeter cube. Now the total charge over here, that will be Q. Of course, here you will have plus Q. On this side, you will have minus Q. They will be equal. So plus Q, let's only take the positive side, is equal to Xn into E into Nd. So this is charge per unit length. If you see the third dimension for the diode, it will be like this. Okay, so if you want to calculate exactly the total charge plus Q over here, you will have to multiply it with the cross-sectional area A. Anyway, if you are calculating capacitance per unit area, then this A is not needed. Okay, so I am removing this A, and the answer will be in uh, depletion charge per unit area. Okay, now this was the case when we were having a, let's assume, reverse bias of VR. Now if we increase, sorry, so if we increase this reverse bias with very small voltage dVr, let's say, what will happen? This junction width will increase with reverse bias, right? Slightly it will increase. Let's assume it is increased by xn plus dxn, and due to that, there will be a positive charge dq, that will be equal to E into Na into dxn, right? Because this is constant. I'm again telling you that if you are calculating or deriving this expression for a linearly graded junction, you must take care of it. So this ENA, that will not be constant, but Na, so this charge density rho, that will be a function of x. Okay, in case of linearly graded junction. Anyway, so this was actually the simple case, and that's why I'm deriving it over here. Likewise, minus q, d minus q is equal to E into Na into dxp, right? Of course, they will be equal. So minus dq, that will be equal to this plus dq in magnitude. So this was xn. Now, if I write it like this, so C as del q by del Vr, because q is a function of xn, these two parameters are constant. You can write it as E into Nd into del x by del Vr. That you can write. Now, how this xn is dependent on reverse voltage, that you should know. So when we were deriving the expression for the junction width, we have gone through, we have already derived the expression for xn, right? So xn was equal to 2 epsilon dpi plus vr divided by q into na by nd into 1 by na plus nd whole root. So this was expression for xn, right? Now we can find del xn by del v vr, right? So because it is the root over here, so you can write as root x to the power 1 by 2, that goes 1 by 2 root x, right? Its derivative. That's why you should write it like 1 by 2 into 1 by 2 epsilon dBi plus Vr divided by q into Na by Nd into 1 by Na plus Nd whole power 1 by 2, right? And then multiplied by, now again we will have to differentiate the whole expression with respect to Vr. So that will be, what is the coefficient for Vr? That is 2 epsilon by q Na by Nd into 1 by Na plus Nd, right? So this expression will be in numerator. So now you can find del xn by del Vr is equal to, let's say this 2 cancels out, and you can write it as uh, epsilon by q into Na by Nd into 1 by Na plus Nd to the power 1 by 2 divided by 2 dBi plus Vr, of course, to the power 1 by 2, right? So this expression we have already calculated. Now we can find the capacitance from this equation. So this parameter is already calculated. You just have to multiply this with E and D, right? So C depletion is equal to E, or we are writing Q into ND into the same expression, right? Whatever this is, just put it over here. So final expression you can write it as, well, this Q is our root over here. So this will come into numerator now. Q epsilon root Na by root Nd. So that will become Na into Nd whole root divided by 2 Vbi plus Vr, that was already in the root. So this Na plus Nd, that will come in denominator. Na plus Nd whole root. Right. So ultimately you can say that this is equal to Q epsilon Na upon 2 Vbi plus Vr Na plus Nd whole power 1 by 2. So this is the expression for this depletion capacitance. You can see that depletion capacitance is proportional to C depletion is proportional to 1 by root Vbi plus Vr. If the reverse bias is actually more than, reverse bias is more than, let's assume 2 or 3 volts, right? 5 volts, then this Vbi will be negligible with Vr, right? Because Vbi generally it is of the order of 0.5 volts, and hence you can neglect, you can write C depletion is proportional to 1 by 2. Likewise, if you are given a problem that if you are given the depletion capacitance, C depletion, at let's assume 0 reverse bias is equal to say 5 picofarad, then what will be uh, depletion capacitance at VR is equal to, let's say, 5 volts. You are given VBI, let's assume you are given VBI is equal to 0.5 volts. So to solve this, you can directly write C depletion at 0 divided by C depletion. So C depletion at 5 volts divided by C depletion at 0 volts, that will be equal to, because it is proportional to 1 by VR plus VBI, right? So that will be equal to root over VBI plus 0 divided by VBI plus 5 volts. So that is equal to root over 0.5 divided by 5.5 volts. Root over 1, right? So C depletion at 5 volts, that will be equal to root 11 times 5 picofarad. You can calculate. Okay. So whatever is the answer. Sometimes it is also important that if you know the reverse depletion capacitance at 0 volt and some given volt, that generally we measure, right, in our labs. So you can find VBI experimental, right? VBI can be found experimentally if you already know these two values. C depletion at 0 volt reverse bias and C depletion at 5 volt reverse bias, you already know. Then you can find VBI, because only unknown over here is the built-in potential. So there are many numericals related to that. Generally people ask. Okay. One more thing, if you are going for not abrupt junction but linearly graded junction, then you must change this, uh, derive the expression, because the charge density, that will not be a step transition as earlier like this, okay, but it will be now linearly graded junction, it will be like this, okay, and then okay, and here it will be xn, here it will be xp. So now the charge, total charge over here, if you approximate it with a triangular wave, then that will be 1 by 2 into E into whatever is the peak value, okay, and max into xn. And even if you, and then you calculate all the derivation. Even if you want to go for a different one, so let's assume we don't know what exactly is, so but you only know the function, okay. So this is your rho x. So to find plus q, that you can say that plus q will be equal to integral from 0 to xn rho x dx, right, of course multiplied by electronic charge. So this is how you can find q and then find the capacitance. But in that case, you also should know the expression for xn, right, as a function of applied voltage VR. So that you should know these expressions are different for different junction profiles. You should go through book and you can Fine. Okay. I think I have completed this. I will explain uh, diffusion capacitance in some other video lecture. Okay. So diffusion capacitance. Okay. So that is your maybe your next video. Thank you.